Welcome to our quantum deep dive.
Great to be here.
Today, we're jumping into something really intriguing. Strange quarks.
Ah, yes, the slightly mysterious ones.
Exactly. And we're basing our chat on the essay Strange Quarks, Rätselhafte Teilchen der Quantentechnologie by Jorgo Schneepaert.
A good source. It really lays out the core ideas.
Our mission today is basically to unpack these fundamental particles, find out what makes them tick, and why they're maybe more surprising than people realize.
Absolutely. And it all starts with the standard model, doesn't it? Our, map of fundamental particles.
Right, the standard model. And quarks are key players in that.
Fundamental building blocks. Can't get much more basic than that.
Okay, so quarks. Remind us, there are 6 types. Flavors, they call them.
That's right. 6 flavors. Up, down, strange, charm, bottom, and top.
And those we bump into every day, the ones making up protons and neutrons and atoms, those are just up and down.
Precisely. They form the bedrock of ordinary matter. You, me, this table, everything.
But today's star, the strange quark, is a bit different. It's the third lightest, Schneepaert says, second generation.
Correct. It sits in that second tier of quarks. And it has an electric charge of minus 1/3 e.
Minus 1/3. So a fraction of the basic electron charge, but negative.
Exactly. Where e is that fundamental unit of charge.
And it's heavier than up and down, but still lighter than charm, bottom, and top.
Yep. It occupies that middle ground in terms of mass among the quarks.
Okay, here's where I think the strange part starts to come in. Unlike up and down, you don't just find these hanging out in everyday matter, right?
That's a crucial difference. You won't find free strange quarks in, say, your coffee cup.
So where do they come from?
They're typically created in really high energy situations. Think cosmic rays hitting the atmosphere.
Okay, like natural particle collisions way up high.
Or inside particle accelerators where we smash particles together intentionally at huge speeds.
Like the LH.
Exactly, those kinds of environments. And even then, they don't usually exist on their own for long. They're part of other unstable particles.
Schneepaert mentions kaons and hyperons. What are those briefly?
They're just other types of subatomic particles, composite particles like protons and neutrons, but they contain at least one strange quark, along with others, and they don't last very long. They decay.
Right. Unstable. Okay, but the name itself, strange. It feels less technical than the others. Why strange?
That's actually a great story rooted in history. It comes from observations made way back in the 1940s and 50s.
What were they seeing?
Physicists were creating new particles in their experiments. Particles we now know contain strange quarks. And these particles behaved, well, strangely.
How so?
They were being produced very quickly through the strong nuclear force, which is, strong and fast.
Okay, created fast. Makes sense.
But then, when it came time for them to decay, to fall apart, they did so much slower than expected for particles created by the strong force.
Huh. So, quick creation, but a surprisingly long life, relatively speaking.
Exactly. This unexpectedly long lifetime, this slow decay, seemed peculiar. Strange, even. Hence the name.
So the name stuck because their decay time didn't match their creation method.
Pretty much. It was a puzzle. And to solve it, physicists introduced a new concept, a new quantum number.
Which was?
Strangeness. They proposed this new property called strangeness.
Okay, strangeness. How did that explain the slow decay?
The idea was that strangeness is conserved, it stays the same during strong interactions, the fast creation process.
Right, so the total strangeness before and after the fast creation had to balance.
Correct. But, crucially, strangeness is not conserved by the weak interaction.
And the weak interaction is responsible for certain types of particle decay. It operates much more slowly.
You got it. So these strange particles could only decay via the slow weak interaction because decaying via the strong force would have violated strangeness conservation. That explained the delay.
That's clever. So this strangeness tag essentially forbids the fast decay route, forcing them down the slow lane.
Good way to put it.
Who came up with this? Schneepaert mentions names.
Yes, the credit largely goes to Murray Gell-Mann and Kazuhiko Nishijima. They developed this concept independently around the same time in the 1950s.
And their idea was pretty fundamental, wasn't it? It wasn't just about these specific weird particles.
Absolutely not. Introducing strangeness was a really big step. It helped pave the way for the development of the quark model itself.
Which Gell-Mann was also central to.
Indeed. And eventually, it became a core part of the standard model we rely on today. It showed there was a deeper structure, more rules governing the subatomic world.
Okay, so we've established they're fundamental, they have this cool history. But why should someone listening now really care about strange quarks if they're not in everyday stuff?
Well, as Yurgo Schnepet points out, even if they're not in your chair, understanding them is vital to understanding the universe's fundamental rules.
How so? Like understanding the strong force better.
Exactly. Studying how strange quarks interact helps us test and refine our theories of the strong force. Quantum chromodynamics, or QCD, that's the force holding atomic nuclei together. It's pretty important.
And Schnepat's essay connects them to some really out there areas too, right? Not just theory.
Oh, definitely. In high-energy physics, places like the LHC are basically strange quark factories in some experiments. Studying them tells us about matter under extreme conditions.
And astrophysics. I saw a mention of neutron stars.
Yes, that's a fascinating, though still speculative, idea. The intense pressure inside neutron stars might be enough to squeeze protons and neutrons into a soup of up, down, and strange quarks.
Forming something called strange matter.
Potentially, yes. Stable strange matter. If that exists, it could change our understanding of these incredibly dense objects. Imagine quark matter existing naturally in the cosmos.
Wow. From particle colliders to the hearts of dead stars. That's quite a range. What about quantum computing? That seemed like a surprising link in the essay.
It is a bit more indirect, admittedly. You're not building quantum bits, or qubits, directly out of strange quarks.
Okay, so how do they help?
It's more about the underlying theory. Understanding strange quarks requires a deep grasp of quantum mechanics, and specifically QCD.
The theory of the strong force again.
Right, and QCD is a notoriously complex quantum field theory. Developing the theoretical tools and computational methods to handle QCD
helps us understand and model other complex quantum systems.
Exactly. The insights and techniques gained from studying quark interactions, including those involving strange quarks, feed into our broader ability to design, control, and understand the complex quantum systems needed for quantum computing.
So understanding the strange helps us build the future of computing, even if indirectly. That's actually pretty cool.
It really is. The fundamental theories are interconnected. Progress in understanding quark physics strengthens the foundations needed for quantum technologies.
It's amazing, really. These particles got their name because they seemed odd, broke the expected patterns.
And yet, understanding that oddness has become totally essential.
Essential for our picture of fundamental forces, the structure of extreme objects like neutron stars, and even for pushing the boundaries of new tech like quantum computers. Yurgo Schnepet's essay does a great job highlighting that reach.
It really ties together how fundamental discoveries ripple outwards.
Well, this has been fascinating. A real deep dive into why strange is actually quite profound in particle physics. Thanks for unpacking it with me.
My pleasure. It's always fun to talk quarks.
So drawing from Yurgo Schnepat's work, here's something for you, our listener, to think about. If observing the strange behavior of these quarks forced us to invent new quantum rules and rethink particle interactions, what other deeply held assumptions about our physical reality might crumble as we keep exploring the quantum realm? What else might turn out to be strange?